Recording is on.
Okay, this is the second lecture in this series. It presents a physicist's view to some problems of biology. In this case, we are going to present a model of cancer. This is a very simplified model. As you know, cancer is a very complex phenomenon. In our case, we are going to present a model in which the starting point is gene expression space. This is to the best of our knowledge, the first time such a model is presented. And we will, in this model, present the progression from the normal state, which is drawn here in this representation, the left area. These are normal samples. Progression from the normal state to the cancer or tumor state, which is the right area here. And we will give some indications or some model to the way in which the progression occurs, or the motion of samples from this normal area to the tumor area occurs. As I say, this is the first model of this kind to the best of our knowledge. There are no free parameters in the model. That is, parameters comes from processing the gene expression data and from compilations in the literature. Okay? This model is kind of simplified, as I mentioned. We are going to describe the progression from the normal state to the tumor state as a one-dimensional problem. This dimension, this direction of progression is precisely the first axis in the principal component analysis of the data, which, as you see, separates the normal from the tumor area. And we start. Okay. This is a conceptual picture. The transition is seen as a discontinuous transition. That is, both regions, normal and tumor, are supposed to be a maximum fitness regions, and in this region a random motion takes place until a large jump move the section or the microstate in the tissue to the tumor zone. These data are actual data for colon adenocarcinoma. We took it from the Cancer Genome Atlas repository, processed this data by means of principal component analysis, as I mentioned already. The positions of the center of the zones, for example, the center of the normal zone is here at the origin of coordinates. The center of the tumor zone is approximately at 156 in these coordinates. And then we can compute the distance between the both centers. We can compute the radii of this sun, the root mean square radii of this sun. And then, as you may see in the actual jump, or the actual distance that should be covered is the minimal distance that should be covered is the distance between the border of the normal zone and the border of the tumor zone. Okay, that is the distance minus the two radii. The reasons for this motion, as I mentioned, this normal zone represents the states or microstates. In the case of colon adenocarcinoma, for example, we can imagine it at the state of crypts in colon. In fact, there are samples, but we can imagine these samples at the state of a crypt, which is independent, evolves independently of the other, of the surrounding crypts, etc. Okay. The reasons for this motion, you can imagine, for example, that mutation cause change in the gene expression, or you can imagine that external factor also lead to these small changes in the gene expressions, or epigenetic event, agents, for example, also. And the reason for these large motions, there could be, for example, large chromosomal rearrangements in which for set of genes is completely removed from the DNA, or you can imagine, which is the most probable cause for these large rearrangements, is that accumulation of a small variation lead to a change of state of a gene regulatory network. Then the first idea with this first statement we want to check is that the motion from the normal to the tumor state cannot be due only to these small random motions. There is necessary to include in the model large jumps. But then first we should check that only small random motion cannot lead to a macro state, a crypt, for example, in colon, to move from this region to this region. Then for this, we should write a kind of a Brownian model, and the model starts from the position of a crypt, of a microstate along this first axis. Then the position is simply the coordinate of the crypt projected onto the unitary vector along this axis. And this is written here. This is a projection. This is the components of the unitary vector, and this is the coordinates of the samples. And then the coordinate is written in terms of the logarithm of the differential expression, that is, the expression of I gene divided by the reference. Okay, then a variation of this coordinate is due to a variation of the expression of genes, okay, as written here. Then these small amplitude displacements can be understood as independent or not coordinated variation of genes. Then most of the contributions cancels out. And then what we have at the end is a Brownian model for Brownian motion, where d is the maximum value of the maximum absolute value of the components of the vector, and du is a random number in -1, 1. That is, this d sets the scale of the motion. Then we can use the usual Brownian theory to write an expression for the risk. The risk is proportional to the number of scripts in the column, of course, or the number of microstates in the column. But in order to make this model suitable to be used in other tissues, we, instead of the number of scripts, we write the number of stem cells, which is proportional to the number of scripts. Then we have the risk, which we will take from experimental data that is in a set of tissues, the number of stem cells, which is also taken from experimental data. Then this d is the, as I mentioned, is the maximum value of the maximum absolute value of the component of the vector. And then r is, as already mentioned, is the distance between the border of the normal zone and the border of the tumor zone. And the only variable remaining here is time. Time, in order to measure time, we use the natural unit, which is the replication time of stem cells in this tissue. Then time is the number of replication of the number of generations. For example, if we have the replication rate, then we multiplied it by age of the patient, and then you get the number of replication, approximately the number of replication steps. Then all the data in this expression is known. The only unknown or free constant here is this constant, but this constant is simply an intersect. If we draw the left hand side against the right hand side, there should be a rect, that is a right line with unit slope, and this is the intersection. This constant that does not affect the functional dependence on these two variables. Okay. Here is the result for 8 tissues. There are, as already mentioned, there is no free parameter in this figure, and then what we obtain is bad fit. Of course, it's not well fit, but the slope, the most important thing is that the slope is near 0 instead of 1, as we expect. This the result is that we cannot model the risk of progression to cancer as a Brownian small amplitude motion in gene expression space, which can be seen as independent or not coordinated variation of genes. Okay, then the next, these are, for example, the parameters. As I mentioned, all these come from the gene expression data processed through the principal component analysis, and this data, that is the number of stem cells in the tissue, the replication rate, the mean value of the risk of cancer risk, lifetime cancer risk, and the standard deviation. All these data are taken from compilations, so that there is no free parameters. Then this next step is to include an additional kind of motions. These are large amplitude motions. As mentioned, this amplitude, these large jumps in gene expression space can be understood as uh, changes corresponding to coordinated or simultaneous displacement of many genes. This of course the result of the existence of regulatory networks in genes. In fact, genes do not act independently; they interact, and as a result, these large jumps are possible. Also, we will model these large amplitude jumps by means of there is a probability is an inverse power of the jump magnitude. This is a kind of Levy or Pareto dependence, which is very common in biology. We will use a guess for the exponent, which is 2, and but I don't believe that it is true important. That is, you can use 1.5 or 2.5. There is no a big difference. The second assumption is that the probability of a jump is low. Then you can write immediately one jump expression for the risk. And in this one jump expression, we make a distinction between, that is, we write more specifically time, and in time, that is in the time steps, we distinguish between the this t null, which is a number of steps in the embryonic period, that is in the period where the tissue is formed. This is important because for some tissues, for example lung, this component of time is even larger than this component of time. And then we made this precision. This is nothing. That is, this expression is parenthesis, is time again. Okay? The lifetime risk corresponds to an age of 80 years. Okay? Again, we plot the left-hand side against the right-hand side, and we should get a right line with a unit slope. This is a prediction if the model works. And indeed, that is what happens. I again stress that there are no free parameters in this figure. That is, the parameters come either from gene expression data or from compilation of data. The slope is 0.83. 72% of the data, the expression is explained by this simple model. The p-value is 0.04. Then, in principle, large jumps in gene expression space may describe the risk of cancer in at least in this set of tissues. We draw also the estimated dispersion of the risk, that is the estimated mean standard deviation, okay? And as you see, most of that, even when considering the standard deviation, they are far from the prediction, from this line is the fit. We understand that these deviations from the fit are mainly due to the fact that we assume that the probability of for the risk is more or less the same for all tissues. That is, these differences are related mainly to the probability of large jumps, which is when its factor is here is because it was assumed that there is these probabilities more or less is roughly the same for all tissues. Okay, the differences here are due to difference in the probability. This is our guess. Okay, as I mentioned, there are no fitting parameters. The small amplitude prominent model is not able to describe the risk. If we include large jumps, that is Levy or Pareto jumps, our formula reproduces the observer dependence. And also something important here is that some data and are posted and the Python routines needed to process them are also posted in this repository. We can perform a qualitative analysis of in a larger set of tissues based on our formula. For this analysis, that is, for these tissues, we do not have this data which comes from the gene expression data. Then we use a common constant which is mu d over r, a common constant, and we shall try to explain why this constant or how this constant vary from tissue to tissue. That is, we give some, let's say, some qualitative explanation of why for some tissues this magnitude is higher or lower. Okay, for example, this is a something which is interesting also to explain, and is the relation the between how our body fight against infection and how fights against cancer. Against cancer. Against there are at least three components or in the fight against infection. There is immunity. There are many ways in which immunity acts. For example, there is a cellular component that is immune cells. There are physical barriers, and there is a numeral component. This humoral component, for example, is very important in bones, these defenses, and in many other situations. In a particular tissue, the relative weight of each of these components varies. It varies from tissue to tissue. On the other hand, defined in the fight against cancer, the main component acting is the cellular one, that is, cells. The immune cells are the main army acting against cancer. Then, for example, in some tissues where the normal functioning prevents a continuous fighting against infection, for example, you don't need continuous fighting against infection in brain or in the germinal cells. Then in these tissues, barriers are enhanced and this component is somehow depressed or diminished. But as a result, the fight against cancer in this tissue is depressed as compared to normal tissues. Okay, this is the kind of analysis which should use in order to explain the observed risk. This is a figure from the paper by Tomasetti and Vogelstein. We have, for example, here all these. First, we have a band of normal tissues. That is a band of tissues where this coefficient in front of time. Notice that in that figure, what we have is the left hand side is risk, the left hand, the right hand side is time, and the slope is this constant mu multiplied by d divided by r. Then this band of tissues is a band where the constant is around is in between 1 and 5. These are, we call them the normal tissues. Notice that there are many tissues in this band of normal tissues. Then tissues that are above, it means that somehow the risk is enhanced as compared to normal. And tissues which are below, which in this case is only one, small intestine, are tissues in which the risk is below. Okay. Then, for example, all these tissues, the risk is above normal because of genetic causes. For example, familial polyposis or a virus also here, Lynch, etc. There are also a few tissues, for example, testicular, glioblastoma, where barriers are very strong in order to prevent a continuous fight against infection. That is, pathogens are do not reach with the high frequency of these tissues. And then, but as a result, the cellular component is somehow depressed, and the risk is higher in this tissue. This is the interpretation for testicular glioblastoma, from osteosarcomas, the in which the how to say the humoral component is enhanced, and the thyroid also have some interaction with the immune system, and the gallbladder, for which the bile has a very strong antibacterial property. Okay. Then this is the understanding of this tissue. Details can be found in the paper. With regard to the small intestine, the point is that the proximity to the colons and the fact that the dimensions are much smaller than the colon makes impossible that barriers will be as large as in the colon. That is, in the border between small intestine and colon, there is a very large jump in the density of pathogens, and probably the distal intestine, that is the region proximal to the colon, should have an enhanced protection because of the large number of pathogen in this area. And in fact, we have there hazard protection. There is a big number of pair patches and number of cells, immune cells, etc. As a result, there is also an overprotection, let's say, against cancer, and then the risk is below the risk of normal tissues. This is more or less the interpretation. Details can be found in the paper, as I didn't mention, but the paper is posted in the archive database. This is a rewriting or an actualization of a very old paper and publish it. Okay. Okay, thank you very much for your attention.